Hello, this video is about stoichiometry, mole-to-mole conversions more specifically. And so I just wanted to go through a couple of practice problems to help give you the idea of what we're trying to do and how we solve these types of problems. So I gave you this sheet in class, and so you can follow along and help fill this in if you'd like. So I'm going to start with number one. And the first thing that we always need to do in these types of problems is to balance the equation. Without a balanced equation, we don't know the relationships between the different reactants and products. So we need to have that first. So I'm going to take a look at number one here, and we have one nitrogen on the reactant side, one nitrogen on the product side, so we're good on that so far. We have one oxygen here, plus two more for a total of three oxygens on the reactant side. But I only have two oxygens on the product side. So what I'm going to do is, in order to try to even that out, I'm going to put a 2 in front of the nitrogen dioxide, the NO2. Okay, so now I have two nitrogens and four oxygens. Well, the nitrogens just kind of got messed up because I have two on this side and I have one on the other side. So what I need to do is balance that problem. So now I have two nitrogens and two nitrogens, as well as two oxygens plus two more oxygens, making four oxygens. The four oxygens over here balance that out, so now I can have a 1 in this central coefficient. Okay, so now that I have this information, I can look at part A, which says 2 moles of nitrogen monoxide will react with blank moles of O2 to produce blank moles of NO2, nitrogen dioxide. So really, I'm just referring to the numbers above it. And so this is just written out as a word expression, a word equation. So 2 moles of nitrogen monoxide will react with 1 mole of oxygen. So I'm going to plug a 1 in right here to produce 2 moles of NO2, nitrogen dioxide. So I'm going to put a 2 right here. So very, very simple, easy as eating pancakes. Okay, we're just going to plug those numbers in. We're just showing the relationship between the reactants and the products. Okay, part B looks much more similar to some of the types of problems that we've been doing over the last few weeks. And so I'm going to ask you the same question that I always ask, which is, what are we trying to find, and what have we been given? So looking at the problem, how many moles of nitrogen monoxide must react to form 4.67 moles of nitrogen dioxide? So what we're trying to find is how many moles of nitrogen monoxide. So you don't have to do this, but I find it helpful if you put your question mark and moles of NO, nitrogen monoxide, equals, and this is where the given information is going to be placed. So what was given to us is 4.67 moles of nitrogen dioxide. So I'm going to plug that in to the beginning of our equation. So 4.67 moles NO2. This gives us a place to start. Okay? So if you take a look at your packet that I provided to you at earlier in the quarter, earlier in the semester, inside of that front cover area, I have a conversion sheet. So last week we were talking about converting between grams and moles, moles and liters, so volume of a gas, moles and particles. Well, today we're essentially doing the same thing, except we're just changing what we're trying to convert between. So it's moles to moles. So when we were converting between grams and moles, we were using molar mass. When we were converting between moles and particles, we're using Avogadro's number, 6.022 times 10 to the 23rd. When we're converting between moles and moles, this is moles of one substance and moles of another substance, just like we have in this problem. We want to go from moles of nitrogen monoxide, one substance, and convert that into moles of nitrogen dioxide, a different substance. And so what we have to do is we're going to use the mole ratio. And that mole ratio is just found in our problem. Okay, so one way to write this is just multiplying by a fraction. Okay, as we've discussed in class, we know the label that's going to go on the bottom is going to match the label that is just before it. So I know that moles of NO2 is going to go on the bottom because I want those labels to cancel out, so I'm only left with moles of nitrogen monoxide. But the question is, what number goes with moles of NO2? So we go back to our balanced equation, and we say, all right, so there's NO2, and it's saying there's 2 moles of NO2. And then we can convert directly over to nitrogen monoxide. So moles of NO, and then we have a 2 that is going to go there because it is a 2 to 2 ratio. And at this point, we can just solve. And I know that it's moles of nitrogen monoxide because these two cancel out, leaving me with moles of NO. Okay, so this is a question that a lot of people start to ask. Is they look at this and say, well, 2 divided by 2 is really just 1. Do I actually have to write that? And the answer is, well, mathematically, no. You could reduce that to 1 over 1, or just 1. But from a chemistry perspective, this equation, this form, what you've written here is a way to communicate with other chemists. So if you don't have the right numbers in here, that other person who's reading this, because it's a form of communication, they don't know if you truly understand the relationship between nitrogen monoxide and nitrogen dioxide. If you just put in 50 over 50, mathematically it's the same thing. But it kind of misrepresents what is actually going on in the equation. So my suggestion would be is go ahead, even though mathematically it wouldn't change anything, is leave it this way because that does a better job of representing what's actually going on in the problem. Okay, so I gave you an example. This could be a good time if you are feeling comfortable with the steps that we've gone through. I know it's only one example, but if you're feeling comfortable with the steps that we have so far, this would be a great time to pause the video and try number 2. Okay, so go ahead if you want to do that. Pause the video, try number 2, and then I will walk through number 2 with you to see if you got the same answers, and if you did, then you're on a roll, and we'll be able to continue on. Okay. So hopefully you tried out that problem. And I'm just going to jump into balancing here, and there's really no wrong way to start. Keep in mind when you're balancing equations that you may have to go back and change once you balance one part. So right now, if I just start with nitrogen, and it doesn't really matter if I do start with nitrogen, it's going to be a little bit messy because I'm working with pens, so I'm going to have to change a few of my numbers. So right now I have 1 nitrogen, and I have 2 nitrogens. So I need to put a 2 in front of my ammonia there to make sure that I have 2 nitrogens on both sides. Okay, so that's a good start. Well, that also changes my hydrogen, so I have 6 hydrogens on this side, I only have 2 hydrogens on this side. So I'm going to put a 3 over here so that now my hydrogens are balanced. Okay, so now that leaves me with a 2, a 1, and a 3, but I haven't balanced my oxygens yet. So on the reactant side, I have 2 oxygens. On the product side, I have 3 oxygens. Now this is going to be a little bit of a problem because no matter what, any number that I put in as a coefficient for oxygen gas is going to be even. And right now, I only have an odd number over here. So the simplest way to do this is, how do I make an odd number even? Take it times 2. Okay, so that's what I'm going to do, is I'm going to take everything and I'm going to take it times 2. So I'm going to take my 2, that becomes a 4. I'm going to take my 1, that's going to become a 2. I'm going to take my 3, and that is going to become a 6. Okay, so now everything has changed, but the relationships are the same. I now have 4 nitrogens, but I have 4 nitrogens on the other side of the equation. I have 12 hydrogens on the reactant side, but I also have 12 hydrogens on the product side. Now my oxygen, I have 6 oxygens on the reactant or on the product side. And that is something that I can get to using this oxygen gas. So I just put a 3 in front, and now my equation is balanced. Okay, so looking at A, 20 moles of NH3 are needed to produce blank moles of H2O. So this is a little bit different than number 1. Number 1 used the same numbers that we had in our expression. But what I'm really trying to get you to do is think about the relationship between these different compounds. So if we have 20 moles of NH3, that's ammonia, we're trying to figure out what that relationship is to water. So some of you may have put 6 down here because you said, all right, up here we just plugged in the numbers that were in our balanced equation. But that wouldn't be right, because then you'd have 20 moles of ammonia and only 6 moles of water. But in our expression, we had a 4:6 ratio. So we have more water. We're producing more water, more moles of water, I should say, than moles of ammonia that is going into the equation. So we want to maintain that relationship. So 20 is 5 times bigger than 4. So logically, wouldn't that make sense that whatever this number is going to be 5 times bigger than this coefficient? So if I have 30 there, then my relationship is still the same. It's 20 to 30 is equivalent to 4 to 6. Okay? So we're just trying to show that there's a relationship here, and so as one goes up, the other one is also going to go up. Okay. After that, we can just solve the same way that we've solved before. So I'm going to ask the same question that I've asked before, which is, what do we want to know, and what have we been given? So what do we want to know? How many moles of N2 will be produced if 3.5 moles of O2 react? So we have our unknown, so what we want to find out, and we have our known value, 3.5 moles of O2 oxygen. So I'll set up the same way that we've done before. How many moles of N2 is equal to, we put in our known value, 3.5 moles of O2. I'm going to write this one just a little bit different. There's not any more right or more wrong than what's above here. It's just another way to write this. And I just want to show this to you in case you see it somewhere else that it's not completely foreign to you. So some people call this like railroad tracks. Just another way to separate out and look at what you are multiplying by. So as we discussed before, whatever our label is on top, that is going to be our label on bottom. So I have moles of O2. Now looking back at our equation, our balanced equation, the coefficient that goes with our oxygen gas is 3. So that is a number that is going to be going into our mole ratio. What we're trying to find is moles of N2, moles of nitrogen gas. So again, we just look back up to our equation, and our coefficient is 2, so we plug that in. Our moles of O2 cancel. And so now you can put in your numbers. So if you can do that math in your head, you're welcome to do so. I'm going to show you a couple different ways that you can plug this into your calculator, because some people are very concerned about how you plug it into your calculator, and it frankly doesn't matter. Many ways it doesn't matter. So I put in 3.5, that's what we're starting with, and I could multiply that by the fraction 2/3. So I can plug it into my computer that way, and I get 2.3 repeating. All right, great. So let's try it a different way and see if we get a different answer. So 3.5, okay. Well, what if I multiply by the top? So that's essentially what's going on is I multiply by 2. Okay, that gives me 7. And then what if I divide by that bottom number? So I'm dividing by 3. I still got 2.3 repeating. Okay, so I'm going to try one more. How about if I take 3.5, and let's divide first this time. So I'm going to divide by 3, and then I'm going to multiply by that top number, which is 2. And I still ended up with 2.3 repeating. So I'm hoping this shows you that it doesn't really matter the order. You just need to think about what are your steps. Because of the commutative property of math, it doesn't matter what order you multiply and divide these items by. Okay. The thing that I am going to be a little bit picky about is even though it's 2.3 repeating, we are not going to be writing all that out. Think about our significant figures. We don't know if this is exactly 3.5 moles of oxygen. It may be 3.48 moles of oxygen. It may be 3.54 moles of oxygen. We just frankly don't know. If those numbers change, then that's going to change what our final answer is. So the fact that I only have two significant figures here, these two numbers don't affect our significant figures because these are exact. These are not measured. We know that it is exactly 2 moles of N2. We know that it is exactly 3 moles of O2. So these are not measured. Because we only have two significant figures here, that means our answer can only have two significant figures as well. And that will leave us with moles of N2. So I hope that was helpful. That's a place to start. And then in class, I'm going to ask you to do 3, 4, and 5 so that I can give you some feedback and make sure that you're on the right track. So thank you very much, and I will see you tomorrow.